Hey guys, welcome to day 12, review continued. Yesterday's review, we took a look at a lot of different things. I want to review today just a couple of things with estimating a derivative, average rate of change, as well as writing an equation of a line given point slope form. So let's take a look at estimating f prime. Usually when you have to estimate a derivative, this comes in the form of a table and also in the form of some contextualized problem. So I'm just going to make one up, a table here. So go ahead and copy this table into your notes. Okay, so here we have a table. I have t values of 0, 10, 20, and 30. I have p of t values of 0.8, 1.5, 3.5, and 4.1. So the context of this problem is the population of a country in, let's say, millions of people. So let's just talk a little bit about that unit here. So P of t is the population of a country in millions of people. So at t equals 0, the population isn't 0.8 people. It's obviously, that would be really difficult to do. It would be 0.8 millions of people, so 800,000 people. T is going to be measured in years since, let's say, 1970. So the t value of 0 there doesn't mean in the year 0, right? We're not talking about biblical times here. T0 means 0 years since 1970. So that first column would read, in 1970, we have a population of 0.8 million people. In year 10 then would mean 1980, 1.5 million people. 20 would be 1990, etc. Okay. So what I want you to do is, given this information, on the test I might also say P of t is a continuous graph. If we wanted to do IVT stuff, don't need to do that here to estimate derivatives. So here's what I want you to do. I want you to estimate P prime of 15. I want you to include units. And then at the end we'll talk about, again, this won't be on the test on Wednesday, but we also want to talk about kind of what does that mean, right? So first off, for estimating P prime of 15, we don't want to just start writing a bunch of numbers, right? We want to start by saying, what are we doing? We're trying to estimate P prime of 15. So let's start with P prime of 15 approximately equals, right? Let's have good notation here. So we give the graders no choice but to give us the points. So this is p prime of the t-value 15. 15 is not in our table if we scroll up and take a look here. 15 is not in our table, but it's okay because we're estimating. We want to estimate p prime of 15. Well, that's simply going to be, we're going to look at the 2 points that surround it. We're going to look at p of 20 minus p of 10, the two y values there, over 20 minus 10. So couple of things to note right now. Make sure you have p prime of 15 and make sure you have that approximately equals sign. That's important because it's letting us know, reminding us that this is just an estimate. This is not a for sure thing. We also need to have a difference quotient. We can have that with p of 20 minus p of 10 over 20 minus 10, or if you wanted to skip right ahead to 3.5 minus 1.5 over 20 minus 10. That's fine. But we have to have a quotient and we have to have a difference. We need subtraction in there. We can't just go straight to 2 over 10. So we've now reached our numerical answer of 1/5 or 2/10, or we could also write 0.2. But we also need to remember to include the units. A lot of people stop when they get a numerical answer and forget about the units here. Well, to calculate these units, right, since this is a rate of change, right, derivative is a rate of change, we're just going to take the units for our p of t function and divide by the units of our t. So again, it's not going to be 1/5 of a person per year. That unit isn't in people, it's in millions of people. So our unit would be millions of people per year. Again, it should not be a mystery where we're coming up with these units from. Think about the 3.5 and 1.5. Those units were millions of people. 20 minus 10, those units were in years. We're taking in millions of people and dividing them by years. So, and then thinking about the context of the problem. What does this mean in the context of the problem? We'll go more into this later as we prep for other things. But this is just saying that in the year t equals 15, which it's years since 1970, so that'd be in 1985, the rate of change of population, the population was growing, because it's a positive number, at about 0.2 million people per year. So that's kind of what we're going for there. But this right here is going to be sufficient for our test on Wednesday. Okay, so that's how we estimate derivatives. Don't forget about units. Don't forget about approximately equal. Don't forget about difference quotient. All those things are very important. Okay, let's look at average rate of change. So this could be a good one for a note card. I noticed some of you guys today in class made some note cards, which is awesome. On one side of the note card, we could have average rate of change of f on the interval, closed interval AB. That average rate of change of f on the closed interval AB is always going to be equal to what can go on the back side of your card, equals f of b minus f of a over b minus a. Now we've done a lot of average rates of change looking at tables, so I just want to do an example from a graph and an example from a function. So let's do the function first. So our function here is going to be f of x equals 3x squared plus 5. What I want to know is, what is the average rate of change? So what is average rate of change of f on the interval -1, 3? I don't think there's an average rate of change practice problem on the review sheet of a function, but make sure you're prepared for this because this could show up on the test as well. Okay? So here's what we have. Our interval here is from -1 to 3. Our function f of x is 3x squared plus 5. So following our formula that we know from right above us, our -1 is representing a and 3 is representing b. So just following the formula here, our average rate of change of f on that has to then equal f of 3 minus f of -1 over 3 minus -1. Again, we see a difference quotient here. If you wrote f of 3 minus f of -1 over 3 plus 1, that's fine. You still have a difference on top. Okay. So taking a look at that, simplifying this out, we are going to need to figure out what is f of 3 and what is f of 1. Sorry, -1. I strongly suggest you find those and simplify them ahead of time, so when we subtract them, we don't have to put a parentheses around that binomial for each of them. So let's figure out f of 3. F of 3 will be 3 times 3 squared plus 5. Three squared is 9. 9 times 3 is 27. 27 plus 5 is what, 32? F of -1 here would be 3 times -1 squared. Plus 5. -1 squared, remember our PEMDAS, -1 squared is 1. 1 times 3 is 3. 3 plus 5 is 8. So, solving out the rest of our equation up here, we know we can put in 32 for f of 3 minus 8 for f of -1 over 3 plus 1 is 4. So we end up with 32 minus 8 is 24. 24 divided by 4 is 6. So our average rate of change here would be 6. There were no units in this problem, so we don't need to consider the units. However, if we did need to, if this is a context problem, our units would simply be the same units that we would get for any rate of change. We'd take the y units divided by the x units. Let's take a look at a quick graph problem. So let's say we have a function graphed here. This is x, this is f of x. Now I want to know, what is the average rate of change of f on the interval 1, 5? Our average rate of change of f on the interval from 1 to 5 would simply be, again, we have 1 is representing our A, 5 is representing our B. We have f of B minus f of A over B minus A, or the slope of the line that connects those 2 points, right? F of B, f of 5 would be 2, minus f of 1 would be -3, so 2 minus -3 over B minus A, which would be 5 minus 1. Notice for average rates of change, we use a solid regular old equals sign because this is the average rate of change. This is not an estimation like we're doing when we're estimating a derivative, f prime. Okay, so solving this thing, we get 2 plus 3 is 5, 5 over 4. We get an answer of 5/4. Once again, there were no units associated with this problem, so we don't have to worry about it. 5/4 is also the exact slope of the secant line that connects those 2 points. Okay. The last thing I want to look at, and we'll wrap this thing up, is very simple. How do we write an equation of a line given a point and a slope? Okay, so if we have a point that we call x naught, y naught, and we have a slope that we're just going to call m, our formula always that we go to right away is y minus y naught equals m times x minus x naught. And we can very quickly go to an equation of a line given a point and a slope. One quick example, let's say our point is -2, 8, and our slope is 4. Our equation of our line would be y minus 8 equals 4 times x plus 2. So again, this is our formula for writing an equation of a line in point-slope form. Thanks for watching. Study hard, have that review sheet. Look at everything by Monday. So if you have any questions, you can ask them. Have a great weekend. I'll see you guys on Monday. Peace.